Let's discuss question number 30 from test 2. This is from strength of materials. So SOM. Let's read the question. A steel rod 4 meters long is fastened to a fixed support A. So you have a support A and you have a fixed support, this thing, and then you have a gap, and then there is another wall A. So this is 4 meters the length, and the gap is basically 0.4 mm. Okay, this is basically the gap. Okay, so you have the gap 4 meters between A and B. So now what we need to do is, so now what is done is there's a gap of 0.4 between the free end and the fit wall B. The temperature is 10 degrees and the temperature has been increased to 38 degrees Celsius. So there is, the rise is basically 28 degree Celsius. The rise in the temperature is 28 degrees Celsius is the increase in the temperature of the, and it's a uniform. Okay, and the values of Fiennes modulus, that is 210 GPa, which is nothing but 210 into 10 power 3, so MPa, so 210 into 10 power 3 MPa. Alpha is given as thermal coefficient of expansion is given 12 into 10 power minus 6 per degree Celsius. Okay, so now let's, because initially, because there's a gap, so there is an unrestrained or unconstrained expansion, and this will not give rise to, and so let's see how much it can expand because of purely temperature rise. So the change in the length due to temperature, I'm just denoting by delta suffix t, is basically your L alpha delta t, right? This is just based on the definition of coefficient of the change in length per unit temperature by unit length is basically your alpha. So that is, this comes from the definition. So length is 4 meters, alpha is 12 into 10 power minus 6 degrees per degree, delta t is 28. So this value comes about 1344 into 10 power minus 6 meters, because 4 is length is in meters, so this comes out to be 1.334 mm. Now meters I can write 10 power 3 mm, so this ultimately becomes 1344 into 10 power minus 3 mm, and that is 1.344 mm. Now the gap is only 0.4 mm, so it can expand up to 0.4 mm without any constraint, but then after 0.4 mm it can't expand because the wall is a rigid wall, it will not allow. So after that, what will happen is there will be a force, compressive force, that comes from the wall B, and so the net deformation is only this. Okay, so it so happens like that. This is your initial state, there's a gap. Okay, so if they would not be having wall, then it would have just expanded this much. Okay, so this is your gap and this is your exact delta t, just, but there is a wall here which basically provides the force, and therefore the final expansion is only this much. Okay, so this is your delta t and there's a delta here, so this is basically the compression which is due to the load developed by the wall, the compressive load has to follow. So I can say that the net expansion is only the gap 0.4 mm. So this delta C is basically provided by this compressive force. It basically, so you can view the problem in this way. There is a free expansion because of temperature rise. It can expand this much. Okay, but only, I mean, this is if you don't have wall. Because of the wall, there'll be it can only expand up to the gap, and after that, whatever expansion which could have happened if there would not have been wall is not allowed by the wall. So this is the compressive delta C is delta T minus gap, and delta T is your 1.34 mm minus gap is 0.4 mm. So your 0.944 is basically is stopped, or this is, or I can view that this is the compression due to the wall developed compressive force P, developed compressive force P, and I can use you assuming elastic behavior. So the because of the compressive load P, the change in length is PL by AE. So this again comes from Hooke's law, because sigma is E strain, sigma is P by A, and E strain is change in length. So from this I got this. Okay, so this is your delta C, which is 0.944 into P by A. P by A, we are asked about stress, so P by A I can put stress into L by E. Okay, so this is basically a stress, so 0.944 into a stress. Length I can use, let's use in mm, so 4 meters, because everything is in mm. Young's modulus will be in MPa, so that directly I'll get stress also in MPa. So this value, if I find out, this value comes out to be, so it's basically 0.944 into 210 into 10 power 3 by 4000. So this comes out to be 49.56 MPa, and so we have options two options have the same value, 49.5 MPa. Now we have to decide whether it's tension and compressive. Now it's quite intuitive that it has to be compressive, because I mean that much length reduction has to be provided by the wall force P, which has to be which is compressive in nature. So 49.4 MPa compressive. So the answer is 49.4 MPa compressive stress is developed because of compressive load P due to the wall. So the answer is B. Option is B. Thank you.